be alright. I'll take it off your mind. Ambition, suicide are the same. Either way, it's gonna take a piece of our life. Caught up in the wave and the shit tidal. When you pull me out the frame and I feel tired of waiting on a day, and I wait on luck until I fall into your lust. In a new place and got the same title. Drowning in grain and got the same silos. Run so fucking deep, fall into pieces in these streets. Yeah, I just learned how to breathe deep. Black nails and a face guard with it. FaceTime minute, send him to a 3-digit guard. Wasting all your time and you don't know who took it. You should get trust with a smile and you don't know it's crooked. I look to the constellations for answers, but you need an appointment for cancer. Booking your caught up in the wave and the shit tidal. When you pull me out the frame and I feel tired of waiting on a date, and I wait on luck until I fall into your lust. In a new place and got the same title. Drowning in grain and got the same silos. Run so fucking deep, fall into pieces in these streets. It's the perfect time to see that you ain't been wasting time with me. I got places I tried to be, 3 cuts deep inside of me. I got pain in 3rd degree. I don't phase my fears for free. Walking through the hall in a semi-single file line. In a high rise, never read the fine lines. Wait, new face, let me put it on. New drug, let me have a try. Same place since a little one, based on a minimum chance that you haven't yet died. Out the box with a brand new mind. I see them walking with no sheets. At the time I'm feeling fine, but I feel the pull of all the street. You're caught up in the wave and the shit tidal. When you pull me out the frame and I feel tired of waiting on a day, and I wait on luck until I fall into your lust. In a new place and got the same title. Drowning in grain and got the same silos. Run so fucking deep, fall into pieces in these.
And we are live for another Flat Earth Friday. How are you doing this evening, brother?
I'm good. I'm excited here. It's going to be fun tonight to smash the globe.
Yeah, so we're going to be doing this with some science-y type things, which I always enjoy. Now, I want to make everybody understand right up front here, we're going to be talking about geometry. You don't even need to know how to do geometry. This is going to be so simple. There's some magic tricks that the space ballers have been using in order to just factor in curvature when it's not there. And we've been doing some fighting in some different forums. We've got some the arguments from the space ballers, and we're going to show everybody the magic trick tonight. Once you see this, it's going to be over, and they won't be able to pull this trick on you again.
Well, they're going to continue to try. And every time we look at all these different quote unquote proofs or theories or anything that they do, you're going to find a common thread with what the proponents of the spear space ball flying through infinite outer space theory is constantly trying to pull the wool over your eyes. They're always, rationalizing something. They're always, adding something and then minusing it. They're always doing some kind of it's there, but it's not there. It's there, but it's not there. They're constantly doing all these different types of tricks. So it's good whenever we can, get that notch in the belt, get that, that come along click back towards our side of truth, and then show everybody really what you need to hear and understand so that you're armed with the evidence and the argument.
Yeah, because it's Well, it's fun to be able to stand on truth. So this group, it's a Telegram group. I recommend everybody. I'll share a link to it in the notes of the show, the description, something like that. I'd like to see other people come in, get involved, and fight for the truth, because there's a rush to it. When you know that there's opponents of the truth out there that are shilling for a spinning globe Earth, and you know the debunks of it, and you can go in there and you can throw these down and make these people run for the shadows, they'll come back with some sort of nonsense. They'll always try to flip and invert something and say you said something that you didn't say. But you can go in there and you can fight for the truth. And these are actual notches that you can always have as far as actually having fought for the truth. So I highly recommend people get queued up on some of these things and get yourself out there fighting for flat earth truth. There's a whole bunch of things that you can be fighting for. I'm just sort of passionate on this topic. I like it.
Yeah, we're both kind of passionate on it. We've always been interested in investigating where we find ourselves as conscious observers. If you're not interested in that, you're in the wrong place tonight. And again, it's really interesting how one side. So Jason and I we don't have a dog in the fight. We're just interested in what we can actually observe and show everybody as what is reality, right? When we started the film, when I figured out that there was clouds behind the sun and the moon, long before I met Jason, it wasn't that I was trying to find some great piece of evidence. It just found me. I was observant and seen it. And what you're going to see is that the other side, right, everything that basically is observable and that we can actually test and verify and repeat, they come up with flipped backwards answers where they try to, play these type of reference games where but this is why. They'll say, we're flying through infinite outer space, but because it's just a constant motion, you'll never measure it or feel it. Everything that they're saying we're on a curved baseline, but because it's equal to the center of the earth, they say that it's curvelled, so that it's curving, but it's still level. So all the time, what you're going to find is they have to rationalize their answers. But tonight, Jason's going to break it down, and he's going to show you in simple terms just what's observable, and how basically you can have the wool removed from your eyes.
Yeah, curved baseline. I want everybody to just stop right there and understand that a baseline can't be a curve. Baseline is a line. A curve is a curve, right? So this is the type of geometry that we all need to be on the same page about. So I'm just going to give you all a quick reminder of high school geometry. There's basically just 4 things that you need to be aware of. And let's start with a point. So a point is going to be something that has coordinates, and it's like really, really small, right? Super small. And so that can isolate a location. You can have coordinates for something with a point. Now, if you put a whole bunch of those points together in a row, now what you're doing is you're creating a line. And if that line is two-dimensional and it stays perfectly straight, right? If you're going to do Euclidean geometry, if 2 of these parallel lines never intersect, now you're a Euclidean geometrist. You've got lines, right? Now, there's something totally different, and that's circles. Circles are really the hardest things for a computer to do because all it is an infinite amount of little points, right, put together at a radius from a certain point. Right, so there is no straight part of a circle, right? There is no baseline. If it's always curving, it's a circle. It's a radius. So we're going to have to really key in on the details of that as we go along tonight. The other thing that you need to know is a plane. Once you have 2 lines that are parallel, you can define a plane. Right? And that's really all that you're going to need to know tonight.
So the reason that I'll just give everybody the cheat sheet, the cliff notes right off the bat, is they say that the baseline is curving, but it's such a small curve that you'll never notice it. So therefore, every single time that where that curve would be needed to be factored in, the data, the measurement for it, when it's not there, they just say, oh, that's because it's too small of a curve, right? The earth is too grand, it's too large. when in actual reality, the Earth is very, very small. We live in a very, very small confined area it's not endless, right? It's very measurable. And so basically, Jason, if we're going to get into the content, I see you're getting it up on the screen now. It's going to be interesting for people. If you have any questions, please leave them in the comment section here or in the live chat. It's better to put them in the comment section below. That way, Jason or I have longer time periods where we can actually give you the attention that you deserve. As well, we're on Telegram in Reality Check and Reality Check chat. You'll find a pinned comment after the video posts with a link there. You can come in and, if you want to debate against this or anything like that, you can have your voice heard.
Yeah, so we've got some slides here that we're going to be going through that are going to help us keep these things on track, well-defined, clear. And I want to point out that, so in the creation of this podcast, I got into some really big arguments with ChatGPT over some things because I was trying to get through the point about how you would have to correct for a baseline changing. And the answers that I was getting from it over and over and over is that the baseline just automatically changes because Earth's a sphere, right? That was the runaround go-to that I was constantly getting. So what I want to do is I want to show that the true arguments from the Spaceball, what it is that they say. I want to show you where that breaks down. At some point, I want to go through and I want to show everybody how, when you ask ChatGPT, how does the baseline change in the Spaceball model? I want you to be prepared for what it's going to do. We're going to go in and we're actually going to do some live contradiction showing. We can pin ChatGPT up against the wall, get it to contradict itself. We're going to show you that you'll never get the straight answer if you ask it, but you can point out the contradictions and come to the conclusion yourself. So to begin with, the baseline problem in the spinning Spaceball model, you have to define the baseline, right? We have to start real simple. A baseline is the reference plane or reference frame from which angular measurements are taken. So examples of this would be a leveled theodolite, a transit citing Polaris, a horizontal reference frame. Can you explain to people what it is that we're talking about right here, brother?
These are different ways where we can verify observations in our reality with measuring equipment.
Yeah, so a transit or a theodolite, it's just like a sextant, except it's on a tripod. All right, so a sextant, you're going to be able to adjust it, look through it, and once you have your crosshairs on it, you're going to have a little mechanism on the side that's going to say how many angles you have tilted it. And so what is the first thing that's done with all of these tools, brother, in order to set them up, right?
They're leveled. They have to be leveled. Put horizontal to the plane of reality.
Horizontal to the plane of reality. And then from there, you can measure an angle up. You can get azimuth. That's when you turn it horizontally. That's going to give you your different compass degree headings. And then the elevation angle is how many degrees above a plane, your local horizontal reference point. All right, so I want to show everybody here, this is the graphic that you will have spinning Spaceballers promoting, acting like this is the way it's real. This is the way it has to work. So let's talk about this. On a flat reference plane, the baseline orientation does not change with distance. On a sphere, the baseline tilts continuously. So what we have here is we have this guy standing at what would be the North Pole on a globe Earth here. And what the meme is talking about is how at this point right here, his theodolite or his transit, whatever tool he was using, his sextant, would be 90 degrees up, pointed to Polaris. All right. Now let's talk about the globe logic here. They take this person, they rotate them over there, and you see what's happening when they rotate them over is the baseline right? The line that this guy's standing on has rotated over here to the side at 60 degrees. What it's done is it's rotated 30 degrees here. All right, now this guy supposedly on a globe Earth, he's going to level up his theodolite, his transit, his sextant, whatever he's using, and he's going to now be plumb to the center of Earth here, and he's going to see Polaris up at 60 degrees elevation. And everybody acts like due to geometry, sight angle is equal to the angle of latitude. And they try to make this just make sense and brush over it like this makes sense, right? Even though these things are not triangulating on something, remember that these are parallel lines, right?
Let's slow it down. Okay, so what we have is an observer at the North Pole, 60 degrees, 30 degrees, and 0 degrees, which is the equator, sighting Polaris. Okay, they're all looking up into the sky and they're seeing Polaris. And you can see right off the bat, due to geometry, you've already got some kind of an explanation or an excuse being made. Due to geometry, sight angle is equal to, again, I'm going to continue to make sure that everyone tuning in understands this. They always have to equal thing. Everything has to become relative. Everything has to be inertial. Everything, all these fancy terms, they come up with these, mathematical equations to confuse you. Okay, but what we're seeing is an observer standing on a sphere, being positioned on the outside of the sphere. And to mention the sphere, it's also perfectly pool ball. There's no topography. It's a perfectly circular sphere. There's no ups or downs. This is just an example of a perfect sphere, which, if you look at the blue marble, the one that NASA showed us, supposedly we're on a perfect sphere when we know that even if it's flat, it's not. And so they're all looking up into the sky, right? And they're sighting Polaris directly above their heads. And what's interesting off the bat is that none of the lines are actually intersecting.
Yeah. So what you have to have is triangulation to the object, and keep in mind just how small Polaris is. So what they get is everybody on the sun example, and they say the sun's 93 million miles away, but it's so big that you have all these parallel lines towards the sun, like you're imagining the entire sky is all sun above you, when it's not. It's just a half a degree of the sky. It's a small point in the sky that you can triangulate to. So they go for these parallel lines, and they hinge a lot of their entire theory on this right here. And so what we're going to do tonight is bust that up. Hopefully everybody just starts getting acquainted with what we're dealing with in the globe logic, right? So the Polaris example, we've got the North Pole, 90 degrees. We've got at 60 degrees north, we have this observer that's they are seeing Polaris at 60 degrees right here. But there is something that has completely been missed right here, and that is the baseline changing from 90 to 60. So the spinning spaceball claim is that proves curvature. Our question, if the baseline is tilted 30 degrees, where is that correction applied? Where is it applied? So let's go to the next slide here. What actually changes in the spaceball model? On a sphere, every latitude is tangent to a different plane. We've got a whole bunch of tools to go through tonight to help visualize all this. Let's start getting them out here and start talking about this. So here's a situation where I've got a guy on the top of a ball right here, and we can rotate him like this. All right, so what we have right now is the guy. I can go to a bigger scene here. You'll see a bit more of it. And so because we have this rotating frame like this, what we want to talk about is how when he's standing up here in this line right here, this is what we're talking about being a tangent. So they say on a circle, these different radiuses go out here. And then if you put a line out here that's perpendicular to one of these, they call it a tangent. So we got to get our vocabulary down on this. It's not that hard. So what is happening here is the rotation is changing the tangent. All right. But what you got to have is a baseline. You have to have a baseline. It's rotating around here. We're dealing in absolute geometry. The Globers are going to try to get you into some relative crazy stuff. We'll be showing you how they do it, how they say it. But what happens is when this person is rotated over here, now the angles are different from that changed baseline. Let me just show you a quick example here where I'm going to bring up the protractor. And so I'm going off of the tangent right here. I'm using this as the baseline. Now, when I rotate off of that, it's showing an angle of 43.1 degrees up to, I just put a ball up here in space somewhere. All right, so we've got 43.1 degrees from this location right here. But now if we take this and we rotate this, so these over here like this, now when we take our protractor, we're going to click on that point where our baseline has changed. It's over here now. We're using this reference point. Now when I look for the angle to this right here, my angle is 2.7 degrees. Right? Because my baseline has changed by 30 degrees. If I went the same 43.1 degrees, that would be up here, right here. Right? But do you see what happened when I changed the baseline? I'm going to get all different measurements right here. So that's what we got to start getting through to people is that baseline changing, what we're talking about there. All right. So on the sphere, every latitude is tangent to a different plane. Level at each point is radial, perpendicular to the radius. That means every observer has a different baseline. That means there is no baseline, right? They've taken the baseline away already. When you say that level at each point is radial, perpendicular to the radius, that means that you're saying that right here, that's level. And if I rotate this, they are saying that's level, that's level, that's level, that's level, that's level. Every single place around the outside of this sphere, they are saying is level. Even though you can clearly look at it and see for yourself that it's not level. Do you start to get the problem, everybody, that a curving surface like this, there's nothing level on it, but they literally say that you don't have to make any changes, no corrections.
So they minus it.
Because the baseline never changes. It's always level.
Treated as a flat plane.
Treated as a flat plane. So the real issue becomes if observer B's horizontal is tilted 30 degrees relative to observer A's horizontal, then their measurements are not in the same reference frame. Without correcting for that tilt, you are comparing two different planes. All right, so there's another graphic that I put up a couple shorts this week, and the one we're going to use for the graphics in it, I think is the newest one that I put up. And yeah, just check this out, everybody. This is going to spell out the issue that we're talking about tonight. We don't need the music. But so what we have is the observer at A, and now we have rotated the baseline by 30 degrees. And so whatever observation this person is getting, they now have to subtract 30 degrees from it because their baseline actually changed by 30 degrees. At the next location, it's changed another 30, so it's 60 degrees. Let's go ahead and give it a little rewind here. So starting to run into issue where you're now starting to look into Earth. All right, it's 60 degrees at this location. The correction that you have to make, because the baseline has come from over here where it was flat like this, and now it is tilted 60 degrees like this. The fact that you have to minus 60 degrees from this angle right here now actually has you with measurements that are putting you into the curvature of Earth for your sighting. All right, and then it gets worse than that. Because you're not accounting for the baseline changing, you get to this position here where the baseline has changed 90 degrees from where you started. So this person's measurements right here, they have to take 90 degrees off of them. Right? And that for something at the horizon will actually point you directly into the center of a ball Earth.
So it's really basic. Okay. The physics, the geometry, the observations, the measuring of Polaris or the sun or any object in the sky when moving around a sphere with a forever changing baseline, you would always have to change your observational angle according to keep, let's say that arrow is pointed to Polaris that Jason has on the screen there. If you put your mouse over it with the circle, that's Polaris. No, right there. So if somebody at 90 sees Polaris at 90 above head, somebody at 60 degrees on the sphere was trying to look at that same spot, they would then have to angle their view down 30 degrees lower than the actual said 60 degree tilt of the Earth.
Well, and here's the thing. Now that we're talking about the actual correction that has to take place, now all of a sudden we have a triangulation. Exactly. Now all of a sudden these things do intersect and you are actually triangulating an object. So, right? The other way, all those parallel lines never triangulate on an object.
And if you're not calculating in the curvature, if you're not adding the data, if you're not measuring it, it's not there.
It's not there. Yeah. That right there is the magic trick that they are trying to pull over everybody's eyes. If observer B's horizontal is tilted 30 relative to A's horizontal, then their measurements are not the same reference frame. Without correcting for that tilt, you are comparing two different planes. You can't do it. So the core logic challenge, ask clearly, how do you compare angular measurements taken from different tilted planes without transforming them into a common reference frame? In physics, you cannot compare angles, vectors, motion, orientation without a defined frame of reference. No shared frame means no meaningful comparison. Does everybody get that if you don't have a defined reference frame, you can't compare two things? So the whole globe thing is they turn the reference frame into a radius from the get-go. They just they start with it and just act like it's there, even though all their measurements are coming from a flat plane, and you're never doing any correcting for curvature with any observation. That right there should set off every red alarm bell that there is. The frame of reference requirement. So for motion or geometry in 3D space, you must define the origin, axis, orientation, reference plane measurement standard, if the spaceball model requires continuously rotating baselines, then those baselines must be mathematically reconciled. Where is that reconciliation step shown in common explanations? The explanations we're talking about are these that
Let's enlarge that graphic as well.
which one?
The one you're pulling up.
Yeah, well, actually, I'm in the full frame right now. I'm sort of doing things out of order of how I had planned.
This one.
Just make a couple adjustments so we can see all of it. So this is the one that you will see shared by the spinning spaceballers. And so this is the one where they assume that parallel lines is a good thing, that we're not actually trying to triangulate anything, and how they move this person over here and then there's never any correction, right? They don't say, well, we saw it at this angle, but because we changed our baseline by 30 degrees, it's actually this other angle line over here. And what they have here is they think they have something against the flat Earth model because they show that on the flat Earth model, when you're at the North Pole and Polaris is 90 degrees overhead, and when you're at 60 degrees, right, and it's 60 overhead, these are the way these things triangulate out. But the missing key is that we all have our own circles of sight, and that each one of these skies that we see, it's based on the latitude that we're at, the tilt of it, and it doesn't triangulate out. It absolutely does not. It only works in your circle of sight.
So it's actually created in such a sophisticated way where it's used to navigate the Earth, right? So the distance you travel away from the North Pole or the South Pole, North Celestial Pole or South Celestial Pole, the lower in the sky that observation point will become. This is how we actually navigate over a flat stationary plane. There's no other way for creation to actually have taken place. It's so well designed, it's so thought out and meticulous that we can just barely articulate the way that it was done. Now, as we can see here, this is the onion coordinate system. So Earth created this reality that we're in, has a coordinate system, right? It has two sets of lines, and within those, you can then triangulate and navigate, right? There's no north is down and south is up, or there's no upside down. Everything is on a flat stationary plane with north, east, and south and west, having you navigate throughout reality. I know some people will try to mock it or say, oh, what happens when you get to the right side, or what happens when you get to the top? So, people have no understanding of how the boundaries actually work. So if you zoom in, Jason, if you wanted to take over, you can explain it. But what I wanted to show people is when you start at the north or the south celestial poles and you see that the direction of their sighting is at 0, you can actually start to understand how the navigation of the reality actually works.
Yeah, just I want to add a little explanation on here. So from the latitude and longitude coordinate system, you can actually find at the equator how many miles is a degree, right? You can find out in nautical miles and statute miles and kilometers, whatever you want. So there's degrees of sky, and then there's a mathematical number as far as distance that's been attached to it. So it's 60 nautical miles per degree at the equator. And so this entire diagram here is to scale, literally to scale. And so at the latitudes north and south of it, the actual distances get shorter. And this is actually the 2D to scale projection of our latitude and longitude coordinate system. So we get up to a point at 90 degrees north and 90 degrees south, and there is no crossover from north to south. These are far north and as far south as you can go. And you're always going to be in between those points at these different latitudes. And this is how wide those latitudes are. And so this is the restraints of Earth. Now we're continue to say it's a virtual reality, but if
the boundaries,
right? But so it does loop over from east to west. And so if you're moving along here, and you're closer to this edge, it's just always centered to where you are, right? That's how you move within it. It's not a pixel for pixel comparison.
So let's really define this correctly. So in actuality, the way that the creation was created was that you're the center of creation at all times. So you don't actually loop. What happens is everything in reality adjusts around you. Sort of like the best way we could explain that is being on a holodeck with a parameter and a set value of borders. The creator hath compassed the borders. He drew it. He decided. He created it. He spoke it into existence. And so we can go and at another time get far down into a deeper explanation of that. But tonight I'd like to get back to, if we could, Jason, if we could start to show the Andrew Marsh depiction of the way that the sightings of the celestial bodies are actually observed.
Yeah, so what these are screenshots from the Andrew Marsh, where this is at the North Pole, at the equinox, and you actually have the sun going around literally at the edge of the plane, where half of the sun is above the plane and half of the sun is below the plane.
That's a problem. That's a huge red flag. Okay, everybody, I need everyone to just take a second here. If the Earth is tilted, so in the globular spaceball model, the Earth has to be tilted at 23.5 degrees. Therefore, we can have the quote unquote seasons. Due to the fact that the Earth has an elliptical path that goes a little further and a little closer to the sun, we get supposed summer and winter, right? That's what they say. Well, if that was true, when you were at the north and south celestial pole or terrestrial poles of the plane or sphere of Earth, you would actually have to have that circling sun tilted. It would have to be tilted 23.5 degrees. The fact that it circles above the ground there perfectly flat, and that's exactly why the final experiment, Will Duffy, which I asked him when Jason interviewed him, why did you not go down to the actual South Pole? Right? Oh, what South Pole, Jason? Obviously the celestial one. We know the magnetic one isn't anywhere near the pole, which also doesn't work on your spaceball model either. But let's look at carefully here what Jason's created. This is an excellent, excellent depiction here. This is brand new breaking Flat Earth Friday content. Nobody's bringing this out. We will be submitting it. Eric Dubé has actually come out. He's looking for everyone to submit all their flat Earth evidence so he can write another book, which is fine. Get the information out there. Jason, explain this, please. This is great.
Well, it's a bonus globe debunk that everybody gets tonight. So, while we have it up here, which can have a horizontal circling sun, A or B? So check this out. All right. In A, we have a Earth that's tilted 23.5 degrees. In B, we have no tilt, and you can see the flat path right here is the only way you could have a sun circling like this. So
the Earth would have to be perpendicular to the vector of the tangent through the center of the sun.
Yeah, so we have the horizontal circling sun right here. All right. In B, this is the Earth with no tilt, and you can see the horizontal circling sun.
Look at how local that sun is in the bottom observer as well.
And A, now we have Earth tilted 23.5 degrees. So even a person that's geometrically challenged, when you look at the model like this, you can see B would be the one, right, that could have a horizontal circling sun. If Earth was a ball, right, and it was spinning, this no tilt orientation would be the one that you could have a horizontal circling sun. But
partially,
if this one,
not not truly, because if you were at the very actual south terrestrial pole, you'd still, so the little slight curvature spinning around backwards, you would lose the sun. If the sun was 92 million miles away, parallel with the center of the earth, the sun would have to be below, it would have to be below the sphere, right? It would have to be under earth, right? Which it's not, because you still have the sun rising over people's heads on the north of the equator during this observation. So as the sun circles horizontally for an observer on the bottom of the supposed space ball, keep in mind, ladies and gentlemen, the sun is still rising over the heads of people in northern Canada. At the very top of the sphere, they still have the sun rising above their heads too. So how is it possible, I ask you, this model does not work? It does not comport with reality in any shape, way, or form.
But still, this is a nice way to really make people spinning space ballers chew on their tongue, and you won't get a straight answer out of them. Nobody will answer A or B, because B obviously is the only option where you could have a horizontal circling sun. That would be with the no tilt. And A, when it's got the 23 degrees of tilt, obviously it wouldn't be a horizontal circling sun if A was, because they're 23 and a half degrees changed. All right. This would be a wobbly path in the sky right here. It'd be tilted 23 and a half degrees.
So is there anybody in the chat that needs this slowed down, looked at? Do you see how this is what we wanted to debate? You know, all these guys, McToon, Jeranism, Fight the Fat Earth, they all run like cowards from us. They won't debate us. All they're going to do is debate someone with a pressurized pizza AE map, United Nations, Freemason, New World Order map model. They won't come at us. They won't debate us. Just this one very fact. Listen, if I can poke a hole in the sphere doesn't exist. Look at the two diagrams, A and B. A, you have a Earth tilted, which they absolutely need in their model to create the seasons. If the Earth was upright, it would be summer and winter all the time for everybody. There would be no further away from and closer to the sun. And no, even though that's crazy because the sun is supposedly 90 million miles away, then they say, oh, it circles further and closer, right? But so the sun is tilted. The Earth is supposedly tilted. That's what's creating the seasons. The Earth is spinning. The sun is supposedly stationary. So what they have is when you go to the two reciprocal poles, you actually have a sun circling perfectly horizontal above the horizon. And now you look at observation B, you have the Earth perpendicular, which absolutely could work if the sun was lower below the Earth when it was circling in the winter, and above the Earth in the summertime. You absolutely could have a sun that was perfectly perpendicular to the plane of reality. But you can't have that with a tilted Earth.
And you can't have both of these. I can't even tell you how many shills wanted to say it's A and B.
Yeah, you can't. Yeah, exactly. It's curving, but it's level, right? It's curvelled now, right? You know, water finds its level, but it also curves. Every single thing that they do, and they come up with, oh, that's because of gravity. So everything you're going to find is, oh, that's because it's an inertial frame. Oh, that's because we minus that out. It's a radius. It has to be. It started off as a radius, just you don't ever calculate the radius because it just is. So I don't know if you want to go to a song break now before we get into the second half.
Well, let's just finish while we're here talking about this, because this is what you were waiting to sort of get into. And so this is the Andrew Marsh. This is showing the elevation angles where what we're talking about is if you set up the surveyor and he's got his theodolite and he's leveled it all up and he takes an elevation angle and the sun is at this angle, right? That'll be at 80 degrees right here on the equinox. If he takes it and it's this angle, that's at 70 degrees because, well, it's 30 degrees up in the sky. And so this is the way the sun changes in your circle of sight. But if you were to actually draw these lines out and triangulate on something, you would actually see that. So all these lines would come together and the equator it's pointed straight up 90 degrees here, but all these other lines would come out and intersect this line somewhere along here in irrational ways. Because remember, at the North Pole and the South Pole, the sun's literally at the horizon doing circles around the observer, half above, half below. And out here, you know, it's pointed up this direction. Out here, it's pointed up this direction. So they do not triangulate. And they're not expected to triangulate because the luminaries are rotating around the observer, rising from the plane. All right, so it's rising up through this plane, rotating around the observer, setting back into that plane in the observer's circle of sight, because Earth is a VR. And the luminaries are set to rotate around the observer.
Right. And if you create a device, right, exactly like this Andrew Marsh is depicting, right, you have a little device that has a circling object on a sphere that you can carry around with you. The Chinese were the first to use one outside of the Hebrew. You can actually use this device that you're looking at to navigate on the flat plane. And it would not work if you were on a sphere. Okay, when you know you're on this latitude, you tilt the device to this said distance, and then you can then map things out using the angles. This is how it was created. It's a completely simple, amazing, and like I said, it takes a lot of thought and study and, you know, over a decade of research to come down to these, you know, interesting conclusions that we've put here. And we're happy to go deeper if anybody has any questions that they'd like to learn or be interested in.
Yeah, we've got Andrew Marsh that, so I was showing you at the, let's go to the prime meridian. We're going to do the same thing here. It's getting me within 1 degree of it. So we'll go all the way to the north. No, this is the north up here. And we'll put this into motion. We'll speed it up a little bit. There's our sun circling right around the observer at the North Pole. And this distance is not all that far. We saw in the south that it looked like the sun was, for the most part, it looked like it was about 15 miles. When you look at the hot spots and stuff, that the sun was rotating around the observers. That would change by elevation, but from most of the footage, it was like that. So then as you go, you know, change your latitude, we're heading south here. Right. Then we'll eventually get down to the equator. All right, it's rotating like this at the equator. And we'll keep taking it down to the south. And this is what happens in each person's circle of sight. This is how the luminaries rotate around you. So it's just one way of visualizing it right here. The other way we've been showing people is by taking snapshots of that, putting it out along the equator so that you can see it like this. Right? All I was doing was dragging my location from here down to here and back up.
Yeah.
Everybody follow that?
Yep. And it all matches from the Book of Enoch perfectly with the 6 gates on the east, the 6 gates on the west, the way that the sun and the moon and all the luminaries travel throughout the sky as a company.
All right. Well, you want to take a break now?
Yeah, let's go. Let's check out this new song about, you know, baseline, the, what is it called? The reference frame game.
The reference frame game. So this should make a little bit more sense to y'all right now. Check it out.
I asked for something simple, something steady, something plain. Just give me one fixed baseline, not a carnival brain. I leveled up my transit, said let's keep it all the same. They said, well, technically it's moving, here we go. You say it's spinning eastward at 1,000 miles an hour, but also around the sun while cosmic forces showering through the galaxy. We're rocketing in flight, but trust the math, don't trust your sight. I just want one point that isn't sliding under me, one straight line that isn't curved invisibly. Welcome to the reference frame game, where the rules all shift but the answer's the same. If you feel dizzy, they say that's fine, it's just another rotating line. You ask for still, they answer with spin. Add another motion, loop it again, round and round till you can't complain. That's how you end the reference frame game. I said, hold on, let's freeze it, pick a place to stand. They handed me a globe and a rubber band. Now stretch your mind, they proudly claim. Everything moves, but it's all the same. North is south and up is down. Straight lines bend without a sound. If plumb lines tilt and baselines sway, it's relative motion, they always say. If every floor is secretly a ride, how do you measure side by side? Welcome to the reference frame game. Pick your spin and rename the plane. If it contradicts, just change the chart. Call it inertial from the start. You ask for fix, they grin and grin. Nothing still, just average the spin. Round and round like a weather vane. That's how you play the reference frame game. Observer A is stationary, but stationary relative to what? Well, relative to observer B, but B is spinning. Yes, but not in that frame. So which one's real? All of them. I'm not confused, I just need one! A frame that doesn't chase the sun! Welcome to the reference frame game, where motion's real but still's a shame. Ask for ground, they hand you space. Stack rotations in your face. If you're disoriented, that's the aim. Just redefine and shift the frame. When steady truth is called insane, you know you're in the reference frame game. So I'll be here with my level and line, waiting for one unmoving sign. If it exists, just say the name, and we can end the reference frame game. Frame game.
I love how fitting that song was for tonight.
That's perfectly said. Let's end that reference frame game. Hey, we're just going to be sitting here with our, theodolites and our lasers and everything we want to look at and measure.
Yeah, we've got all the toys up to play with tonight. So we've got this is the 2D onion showing the way the circle of sight, the way these elevation angles change on a plane. This is the answer to this.
We're going to make sure you zoom in more on that diagram so everyone can clearly see it, please.
This is the answer to this. The top portion here. So Polaris is seen at a height angle equal to the latitude of the observer. The slight lines would all cross at the position of Polaris, but they don't on flat Earth. Flat Earth model is wrong. No, this is exactly how it works. And so that's what we're showing when it comes to
this model.
This model. like this. All right. So we absolutely do understand that they don't triangulate. There isn't a sun out here floating above Earth
So
3,000 miles high,
no,
right?
or a moon, or the stars for that matter, because they're actually fixed to your location depending on your elevation. That's the thing. The higher you go in altitude, the further the moon moves away from you. Okay. When we see a sun going behind a plane, the people on the plane see the sun further away from them. So everybody has their own vantage point inside of this reality. Okay. And this is how it actually works perfectly. And it's funny because even in their own model, when we go back to it, right? Your diagram, let's go to their section. It's not pointing at the same place in reality either. And
No,
on top of it, they've got the junk curving. They got everybody on
yeah.
the side of a sphere, like, hey, we're looking over here. And they're all pointing to arbitrary spots that wouldn't be aligned to where a central North Pole or the sun or the moon would actually be.
Just imagine if this wasn't something like Polaris, where they say it's trillions of miles away or something like that. Let's just say that it's a hot air balloon, right?
Way up there.
That's floating right up here. Well, you have to triangulate it, right? This person has to have an angle that points to it this way. This person has to angle that points this way. And then those people would need to know how much the baseline changes between them.
Mm-hmm.
And then they would be able to triangulate something. And then the lines would intersect.
Red's retarded and Double D Hubbard could get in their cars and they could drive to the different latitudes and they could measure these things and they could say, yeah, after I adjusted my 30-degree baseline shift, I absolutely triangulated with what Double D Hubbard was saying he was getting on the 90th and me on the 60th. But that is not what we actually measure in reality. And the fact that their model actually has, people upside down, raining and snowing and all the oceans and like supposedly this giant continent of ice floating upside down. And when you get them on that and they say, oh, that's because of gravity. This guy, Cavendish, he, hung 2 lead balls from a shed, more balls again in their up reality. He looked at it through a window with a telescope and he could see that those balls moved like a millimeter closer to each other. And then he weighed everything in the known universe off of that sighting. That's how we believe that the sphere Earth works. Again, if we are looking at 2 different observations where neither of them triangulate, if Occam's razor is to be taken for what is true, the flat, still motionless plane, the 2D coordinate grid that Jason's showing with the Andrew Marsh on top of it, where we would easily be able to navigate, wins the debate. It's more observable. It's more what we test. If we all observe and see Earth as a flat stationary plane, we can't say, oh, but it's got a radius because the width of the plane itself is halved. Now you're telling me that it's a sphere because you took one measurement and then you've created a radius from it, and then you put that into every measurement that you do, and then so everything that we say, you say, oh, that's a sphere because you've pre-assumed a radius off of a measurement that you take from one side of reality to the other.
Yeah, should we show people how ChatGPT, how all these different things?
Well, are you through your
actually,
slides?
I might not be through the slides. Let me
look at the slides still.
So, yeah, we were at the spaceball model requires a continuously rotating baseline. There is no reconciliation of that ever. The surgical question, instead of arguing, show me the coordinate transformation step. All right, that's just it. Bingo, bango. If somebody's telling you the baseline changes, show me the coordinate transformation step. That is, if the Earth is a rotating sphere, show the transformation matrix, show the angular correction. That means that at every single different latitude, somebody's got to say, okay, well, whatever measurement you got there, subtract this amount from it so that we can compare it, because I'm 60 degrees different baseline to you, right? That's the way every single measurement would have to be done in the entire world. Somebody would have to say, okay, I'm at this latitude, you're at this latitude, so you have to subtract, but no, you won't get that from the AI bots and all that kind of stuff. We'll show you what you'll run into. So So show the angular correction, show how one baseline is converted into another. If none is shown, then the comparison assumes a shared plane. Where is the coordinate transformation step in any comparison of two different baselines? We're talking when it's two different locations. Where is the information where somebody is saying, listen, your baseline changed by X amount from my baseline. So you have to subtract that from your measurement.
SketchUp model shows it better. It's got much more lines and tangents and angles.
We'll go with this one.
Yes. These are all measurable, right? Like Jason showed earlier, measuring the little sun that he has. Show us the steps in the transformation matrix that would absolutely be data collected if we were on the side of a sphere.
Yeah, it's just common sense that if you take a measurement from this location right here, and it's whatever angle they say, and then you want somebody else's measurement, let's say they're over, over here, like that. All right, well, go ahead and get out your protractor. You're gonna set it down here. Remember, your baseline has changed, so we're using this here as the baseline. Now all of a sudden, the angle from here over to here, it's a negative.
To look through the Earth. Okay, but
it's a negative.
This is what they do, ladies and gentlemen. They are always accusing us because they create straw man arguments. They create things that aren't real and then debunk them. They're the ones who are literally moving the luminaries. They have to move them to absurd distances that isn't even fathomable to the human measurement or mind, right? They're supposedly like trillions of what they call light years, right? That's not even something that you can measure. Show me a light year on a tape measure, please. You can't. Okay. And that's how they're able to do it. Every time they've taken a few thousand years, they've tried to flip things upside down. They've tried to invert what is reality, and they continue to move the luminaries. Oh, the reason why. So what about the local moon, right? How come nobody has to correct? Oh, they say, oh, well, it's because the face is upside down, right? That's how that proves you're on the bottom of a sphere, when in actuality, that exactly shows what we've been showing with the 2D coordinate system. How there's
it also shows that the moon is two-dimensional.
Yeah, I mean, there's only one face. No one's ever seen the side or the back side of the moon, ever. If I had my bell, I'd be ringing it, right? What we have is a rotational heavenly bodies that acts in a spherical way around the observer with 6 gates in the east and 6 gates in the west. And it moves throughout the plane as you move, keeping you at the center of creation. Creation was created for you, ladies and gentlemen. It was created for me. It was created for Jason. It was created for all of us to have this immersive experience inside of a supernatural realm. Okay. It's not some spinning ball you just came into existence from an explosion of nothing that turned into complete time, the most intricate, complete, way more complex than the fanciest stopwatch ever even thought of. It didn't just happen randomly, okay? And the properties of Earth is that it's flat and it's stationary. Can we get back to the slides now? This is such a great night tonight. I hope everybody tuning in is enjoying this. This is what we're here for. This is what we're here to do. Investigate reality together. Jason's put together these slides. Number 7, perspective tie-in. Jason, can you tie this perspective in, please?
Yeah, so we'll do a little bit of a motion demonstration here. So it's pretty incredible that we have tools right now that can show us exact positions in 3D space with lighting, with shadows, and with motion timing, all that kind of stuff. We have those types of tools in our hands in the year 2026, and it's really incredible. Let's get to a large share here. And so this motion tool right here, you can put whatever graphics you want in it in 3-dimensional space, and then put a camera in the scene and move the camera in the scene, and that'll end up being your footage. All right. So this is the digital way of recording movies. And the entire environment is built off of planes and perpendiculars. All right. This is the hardest thing for a computer to do is circles, right? Because it just basically comes down to your resolution. But there's a number of things I want to point out right here that drive the Globers wild, and that is actual perspective. Let me bring this down just a hair so people can see this.
Real perspective that we can observe and replicate inside of a modeling program.
Yeah, so actual perspective, when perspective is being used, right, everything converges to a horizon. Now, if I turn this to an orthographic view,
that's the globe earther's choice of reality, which is not observable. You have to
right,
take
now
yourself outside of the actual reference frame.
Now, all of a sudden, all these surveyors that were getting smaller off in the distance, they're all exactly the exact same size now. And it doesn't matter how big this scene is, I would still be able to see these. I could move the camera back further and further and further and further. And
it's all perpendicular. They're all perfectly parallel. They're all equal in size, equal in height. Nothing's rising or lowering. Nothing's going beyond the vanishing point, because that's not our actual reality. That's not how we view things in actual reality. This is a creator view.
Yeah, it's like in a blueprint. When you have blueprints for a house, you have side elevations. So this is a side elevation, an orthographic view. But as soon as you add perspective, right, everything converges where all the lines, all parallel lines come together at a point,
a vanishing point
at the horizon, and they disappear there due to things like angular resolution. So what will happen here in this scene is if I keep zooming in here and show you all these different
more colors are showing up in the view. Wow.
Yeah, so I'm driving the camera forward here, and you're seeing all these different surveyors. Now, you couldn't see all these surveyors before. You're only able to see them now because I'm getting close enough with the camera.
They're now inside of your circle of sight.
Yeah.
Just terminated at your vanishing point.
Now what I can do is I can move backwards away from this.
Disappearing from the bottom up. And this works perfectly on a flat and stationary plane, not on a sphere. Because if it was a spherical plane of reality, things would actually be bending and curving away from you as the observer. So you would see the tops of people's heads as they were going beyond the horizon.
So I'm getting farther and farther away. And as I get farther and farther away, guess what'll happen?
It's going to disappear.
The entire scene right there will eventually disappear, because what'll happen is there'll be nothing that is the size of a pixel anymore. So there'll be nothing left to render.
It becomes unresolvable.
So if I'm up above this whole thing like this, and I can see it all now because I've picked up so much elevation, I can still back away from this far enough that I'll get to the point where something is no longer resolvable anymore. So even if you weren't too high, you would get to a point where you couldn't see Earth anymore. Looking down at Earth. All right, because you get to a point where the pixels become too small, and you'll get to absolute blackness. So you go farther and farther and farther away.
This is the properties of the way vision and all observable reality works, including there's reasons why when you go up high in an altitude, everything goes black. Even in the daytime, ladies and gentlemen, the sky above Earth is black. And if the sun was 92 million miles away, it would never be black in the sky. It would always be lit, right? You got the sun, then you've got black sky above it.
But I want to show everybody, so every single object in this 3D space environment has an X, Y, and Z position. It has an X, Y, and Z rotation. These are the 6 DOFs that we put out a video about recently and we're talking about. This is the information that has to be present for anything in any model. It has to have the XYZ coordinates for position and for rotation. And then if it's moving, right, you'll have a stamp right here that shows it at a certain point, it's at this position. And then you'll have a certain amount of frames, time, seconds that take place. And if you put it to another position, and then when you hit play on that, that translates to motion, right? So those are the things that are required, and it's all based on an absolute reference frame. So this right here, the model has a reference frame in it, right? It has a plane that everything's being built off of and oriented. You start out with the plane, and things are either above the plane, below the plane, and those XYZ coordinates tell you exactly where something is in 3D space.
You absolutely have to have them to have something within the 3D space. You can't have something that exists outside of them inside of reality. So if something doesn't have those coordinates, it doesn't exist. That's Earth's, rotation, direction through infinite space, the sun's direction and rotation through infinite space, and then the whole entire Milky Way galaxy and its supposed movement. We're going to crash into the Andromeda and all this other nonsense, this great Milky Way. Everything that they tell you is built off of a fairy tale of a fantasy to actually create, so much error in you. If you have a worldview that's created about, monkeys came from nothing, what do you think that does to you as an eternal being? What do you think that does to you on a subroot level?
All right. So that was a perspective view. It wasn't the actual camera. So the camera has the resolution lock on it. I was wondering why I was still able to see it. So now I'm on the camera mode, and let's go ahead and turn this camera so that we're looking down here. And
I already lost it.
Yeah, I already lost it. So that's the edge of reality for this camera right here. It can't see anything more than that.
And if you've seen any high altitude footage or anything like that that's just amateur, this is absolutely the way that it works. This is what we record. This is what we observe. The black sky takes over. The higher we go, the less we get to see. We don't see more land. We're not seeing, and anyone that tells you they see more, what they're actually doing is parenting NASA nonsense, who thinks they can see to the ends of the universe, right? They think they can see too far, not us. We know the amount of resolution that we have is very limited.
Yeah, angular resolution cuts off things because it just gets too small for something to see. You can only see something that's so fine, so tiny.
You want to back up a bit with the view?
Then it disappears. Yeah.
Show everybody how it disappears. And then we'll go back and tie all this together before we go to our last points of the, amazing luminary parade. We also have a crazy Selenian eclipse taking place. We got to touch on those before we end the show. But as you can see here, when you back away from objects at a distance, they too disappear, right, on a flat plane. A little hard to navigate, but you can see there's much less colors on the floor.
Well, and that back line will just keep shrinking.
See, you can see yellow, everybody. Now you can see pink. Now you can see purple. Now you can't see, you're at blue. This is the way reality works, whether you're moving forward or back or up or down.
Now we cannot even see that very first surveyor.
It's gone. And this is what we can observe in reality, ladies and gentlemen. You're never going to go up in the sky and see a sphere. Okay. Only in Hollywood are you going to see that. But what you are going to see is exactly what Jason is showing you right here. Whether it's with a high altitude drone, whether you're in those planes, what is it, the B-2? Whatever it is that you're going up in, this is what you'll actually observe.
Yeah. So just wanted to show everybody the limits of resolution, right? Even in a computer, on a perfectly flat pane, you can't see forever.
No.
You literally can't.
The only people that tell you that want you to believe you live in a side-on orthographic non-reality creator view.
Yeah, as long as perspectives at play, your vision will terminate in a circle of sight, and you won't be able to see any farther.
That's correct.
So, all right, what else do we have here? We've got...
There's a closing statement.
Yeah.
Number 8.
If there is no correction for a changing baseline, then the baseline is not changing. And if the baseline's not changing, you're on a plane.
But I mean, it's simple, everybody. It's simple.
Here's the globe version that we've shared before. And it's these. So if the observer's at the equator right here and he sees, something 90 degrees above him, and then somebody is at the same longitude, but 10 degrees different, and they see something, well, their baseline changed by 10 degrees. So whatever measurement it is that you get when you level out because you're changing your baseline, then you have to correct for that. And as soon as you correct for that, so each one of these, you can see where the sun is right here. This black line is the amount of correction that you would have to make at each one of these locations. And so this is the way it triangulates here, where out here, your farthest triangulation is at 3989, just short of 4,000 miles right here. And then each one of these are closer and closer triangulations. Then you literally start getting their triangulations where it's triangulating inside Earth until you get to the point where your North Pole and South Pole here, you have to subtract the 90 degrees. So they're both pointed towards the center of Earth right here.
I mean, it's so funny to imagine, like, if you had an elevator, at what point would you be upside down? If you were flying from Antarctica to the North Pole, like, would you flip up right? I mean, the whole idea that we're living on a giant spinning space rock is just hilarious, everybody. Come on. Like, you got to hand it to these, fallen ones for trying to pull the wool over people's eyes for so long.
Yeah. So do you want to go through?
We can touch on it.
Chat.
I think we might be running a bit short on time for that, but if you want to, it's just you just do if you want to do a quick demonstration of how it's going to fight you.
Well,
it's just going to give. So ChatGPT is good for a lot of things, but it will argue and come up with nonsense answers at the same time. You have to be calculated and careful with it. That's what we wanted. You wanted to show people, right?
Yeah, I just want to show everybody's. Let's ask the question. So, how is it that the baseline does not change for observers on a sphere? And you're going to get a response. Physical baseline from geometric reference. On a sphere, the local horizontal plane absolutely does change orientation from place to place, but the comparison of Polaris angle does not require correcting that tilt because the geometry already accounts for it. Let's walk it cleanly, all right?
Oh, hang on, let's just slowly go through that point. It says that it absolutely changes, but it's the geometry. Again, they add the change, and then they simply just minus it out because they say geometry.
Yeah, they're saying it absolutely does change from place to place. All right, so does the baseline change on a sphere? It's going to say yes, locally. On a sphere Earth, level is tangent to the surface, vertical is radial towards the center. So if you move 30 degrees in latitude, your local horizontal plane rotates 30 degrees relative to someone who stays behind. All right, that part is not disputed. Why no extra correction is needed? The reason no separate correction is applied is because the measurement itself is defined relative to the local vertical not some remote observer's plane. So
It's all
what they've
relative.
just done, if they've stopped comparing A to B here.
Yeah, it's not comparable. It's relative now.
Yeah. So you measure the angle between your local horizontal, let's get down here to where the apparent baseline problem comes from. Each measurement is local. The latitude relationship emerges from a central angle between the two radii, not from comparing horizontal planes directly. So what they're saying here is that on this model,
It's parallel.
when you rotate this guy, right, when you rotate this guy, that right here, it's level. 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 All the way around here, it's always level. So you do not need to make any corrections. It was level the entire way, right?
Let's really drill in on this. If you have a device that tells you level and you start going in a direction and nobody told you the shape of the reality you were in, and that level never changed, which shape are you above?
That's a plane.
That's a plane. The only way you'd ever be on a sphere is if all of a sudden that level changed. You're now on the side of a thing. Each degree we go around it, I'm another degree off. I'm another degree. I'm upside down on this thing. Oh, we live on a sphere, everybody. There'd be no denying the evidence. Case closed. Let's move on. That's done.
They do the whole thing without ever changing the baseline ever, because they say that, oh, it's just a tangent and that makes a circle, and and because of that everything's level.
Curvature. Again, if Jason and I both have a device that levels out our surroundings and we go each our separate ways and we meet up again at the same point going opposite directions, just because we meet up again does not indicate that you live on a sphere, especially if you're using a measuring device that tells you that the ground beneath you is in fact level the whole entire direction that we travel.
Yeah, a true level, an absolute level. And we have an absolute reference frame. These are the things that spaceballers hate to hear. They want everything relative. They want to change the reference frame to make it spin. They make the reference frame spin. They make Earth still so that they flip around the reference frame. When you hear people talking about the changing of different reference frames, and saying that it's just level everywhere, right? Just understand that you have to. You literally have to make corrections in order for there to be curvature.
So what Will Duffy and I don't want to call him Wolfie. I want to use a funny name. They took the observer here as the man and they put a level here, and then they started spinning the sphere. They said, see, everywhere on the sphere is level, as they were spinning the sphere above a stationary level that they held above it. And they were like so duping delight. Oh, we're so smart. We figured it out. Look, they're spinning the sphere and they're holding the level, showing you everywhere is level. But in reality, if you take that level and you go around on that sphere, you're going to realize one thing right away is that bubble is showing you that it's not level on the side. You're upside down on the bottom of it.
Absolutely. Well, is that
there's probably the two articles to look at before we close out.
That's right.
Yeah, we want to make sure everybody's aware tomorrow night, if we're going to start with that link. I don't know which link you have up first. Take it away.
First one, we've got a luminary parade coming up, everybody. Check it out. Probably tomorrow morning, right? After this podcast, when the sun comes up, beat it and you'll be able to check this out. Play. If it
Right,
plays.
first up, let's talk about the planets, because as we get towards the end of February, you're going to see a lot of people and news outlets talking about what's been dubbed a planet parade or planetary alignment, where 6 planets are visible at once in the night sky. Mercury, Venus, Saturn, and Jupiter with just your eye alone, and then Uranus and Neptune you can see with a telescope. Now that is true for the rest of February and into early March. So this is not just visible on one night, but I've still seen a lot of media outlets covering this, already stating this planetary parade will be on the 28th of February specifically, which to me is honestly bizarre. I don't know where that date has come from. The only thing I can think of is that the 28th is a good balance between Venus rising earlier each night and Mercury setting earlier each night. So you've got a good chance of actually spotting both. Now let's just do some quickfire FAQs on this planetary parade. The parade or alignment name comes from the fact that yes, they're all in a line on the sky. That's because all the planets in the solar system orbit in roughly a flat.
No, it's not like that. Flat, yeah.
They all along.
The luminaries travel all within this yellow path. That's right here.
That area there. The ecliptic, the line that goes out through it. All of the earth that was written about in the scriptures 4,000 and 5,000 years ago.
Plane, but that doesn't mean they're all lined up in space. It just means that they're all over on the same side of the sun as Earth.
It's not like that. It actually means that.
Huge debunk. You shouldn't even be able to see Mercury.
It means that they are all in a row where, is it the rising or setting that we're seeing in these?
Setting. You can go out and see the luminaries already tonight. You can go out and see them. If you can find Orion's belt, just look to the setting side, to the west side of Orion, you're going to see it.
Yeah, so when you're out there looking, they're all in a path in the sky.
On that side. The other side of the diagram. You're on the east. Now you got to flip the wrong way again. Everything confusing.
Yeah, I was in the south, so that threw me. All right, so here is the path for us. You'll see them in a row going down like that.
Yeah, on the far side of the yellow area there.
Yeah, over here.
You'll see it, and higher up, starting at 3/4 of the way up. Then you'll see all the luminaries coming down. And if you want to be able to find it perfectly, when you look up to your left, where Jason's cursor was, around between 13 and 14, you should see Orion's belt. In the northern section of the Earth, you'll see the distinct 3 stars that make up his belt. And you just look around from there towards the horizon, and you will see the different. And planets actually just means wandering stars, right? In Latin and Greek. Doesn't mean solid terra firma spherical Earths flying around in the outer space. It's luminaries, lights in the sky.
Can't find my time. The time is missing from the screen. I was going to show it.
It's not a big deal. I want them to go out and look for themselves.
Really all right.
In their orbits. It's only Mars that's still on the other side of the sun from Earth so that we can't see it. This also isn't that rare. The last time this happened was February 2025, and before that, back in 2022. So if you have a clear night around the end of February, you can enjoy this planet parade.
Orion's belt right there.
Be aware, unless you have a very clear horizon in the west to look towards just after sunset to spot Mercury, Venus, and Saturn, I'm talking no trees, no buildings, no mountains, no hills in the way. The only planet you'll be able to see with just your naked eye later in the night will be the very bright Jupiter, which we're going to have in our skies for a few months yet. All right, first up.
Nice.
All right, so that is the luminary parade. And the other thing, which is really cool, is that the blood moon that's coming up this March 3rd is going to be a selenion. I think that's how you selenion.
It says selenion.
Selenion. So this is really cool because
Senililion. Sorry, I'm saying it wrong.
It's a rare sky event where both the eclipsed moon and the sun appear above the
What?
horizon at the same time.
Get out of here. Another globe glurf debunk. Thought it was the Earth creating the shadow on the moon and between the sun, Jason, to make the supposed eclipse. Everyone says, I know the Earth is round as a round shadow on the moon when the Earth eclipses it from the sun. Well, how is this junk taking place if both are above the horizon, ladies and gentlemen?
Ooh, how do shadows work? Yeah. You can't have a shadow off of something that's not in between the two, right?
Uh-oh.
If they're both above the horizon. So yeah, that's pretty awesome. That just the far east coast of the United States will be able to see both the sun and the moon above the horizon. But another wonderful heliocentric debunk.
That's
right
going to be
there.
March 3rd. And sadly, I do believe that, I guess it's Wednesday, Thursday, they're expecting a lot of rain. So they might, totally clog up the sky so that nobody can see this. But I'm praying and hoping that somebody on the East Coast can film both the sun and the moon above the horizon with the eclipse taking place.
You know what I thought was hilarious is that the Globers do so little to push this selenial lion because it is a debunk that the reference that they have here is a flat Earth reference.
Unbelievable.
This is ChatGPT sourcing.
So yeah, the flat earthers told you they'll both be above the horizon. The selenial lion occurs during an eclipse. Hilarious.
Yeah.
Amazing.
All right. Well, I think that's the luminary updates for this week. Anything else, brother?
Yeah, just everybody be prepared. Anything could take place. We've got some interesting stuff going on right now with World War III kicking off very shortly with the whole supposed attacking of Iran. I don't know if there'll be After the Noise coming up soon. If not this weekend, there guaranteed will be one next weekend. Thanks everyone for tuning in. If you have any comments or anything like that, please leave a comment below. Super shout out to the Goldsmith. Always finding some great new music. Good job on your part today, Jason, for creating some music. Thank you to YD. Thank you to everybody that shows up in the chat and everybody that has a comment below. Go on and tag your favorite glurfer. Whoever thinks they believe in the globe, whoever thinks that they know everything, go and send them this link and tell them they know nothing.
All right. Well, where's the only place people are going to get this content, brother?
Only on the How Shy News networks.
Endless night, the silence binds my soul.